why don't we get started? Well, I hope you have all had a chance to fuel up and add a little energy to your system, and we're gonna move on. And let me say, rarely do I get to introduce a speaker where I can simply use his first name. I have never had the honor of introducing Cher or the performer formerly known as Prince. Our next speaker, though, is one of those that gives me this opportunity, Amory. Amory, who brought us the Negawatt. Amory, who has written 31 books, including his recent one, Reinventing Fire. Amory, who dropped out of not only Harvard, but Oxford. Amory, who was a fellow here at Dartmouth. Amory, who Time magazine named one of the 100 of the world's most influential people, and a longtime friend and colleague, Amory.
Well, thank you, Dan, and after that gracious introduction, I can't wait to hear what I'm going to say. But I will try to fill the main gap in our conversation so far today, namely economics and competition, and thus to explain why I think new nuclear build is uncompetitive, is not needed to back up or to outpace the growth of much cheaper alternatives, and is not an effective way to protect the climate. So, in my mind, the argument doesn't get as far as arguing about whether it's safe and non-proliferative. Now, Peter Bradford referred this morning to the prevalent myth that nuclear power was flourishing until the 3 Mile Island accident. And as you can see from the NRC's records of both orders and construction permits, 4 or 5 years before the accident, the U.S. nuclear orders fell tenfold and never recovered. There's a definitive causal analysis by Kumi and Hultman showing that with this graph that 2/5 of the nuclear cancellations occurred before 1979, leaving many other units kind of teetering on the brink and soon to be canceled as well. But the bad economics that made nuclear power fizzle are explained in Business Week's 10-page cover story on Christmas Day 1978, 3 months before the accident. It began by saying, one by one, the lights are going out for the U.S. nuclear power industry. Reactor orders have plummeted from a high of 41 in 1973 to 0 this year. Actually, there were 2 more, the last ones just days later. And it found that for lack of a business case, the U.S. nuclear industry is apt to contract dramatically and it may collapse altogether, which is exactly what happened. A new myth that a vibrant global nuclear renaissance was cut short by the Fukushima accident is equally widespread and equally false. Global nuclear retirements had already exceeded additions for 2 of the 3 years before Fukushima, again due to bad economics. So let's look at the economics. We'll start with operating costs because reactors are promoted as costly to build but cheap to run. Yet, as Daniel Allegretti ably described earlier, many existing and long paid for U.S. reactors are starting to be or at risk of being shut down because just their operating cost can no longer compete with the typical band in here of wholesale power prices, typically depressed both by gas-fired plants and by wind power. So this graph from my Bulletin of the Atomic Scientists article a year ago, and it summarizes nuclear industry data on the operating costs of all U.S. pressurized water reactors, both within each of and between the 4 quartiles for 2009 to 11. Each quartile has 25 plants or units in it. The operating costs vary quite widely, especially because of major repairs and renovations, the so-called capital additions shown appropriately in gold. And they're called net capital additions because they're capitalized rather than expensed. Those expenditures may fix failing old components, they may invest to increase the unit's output or lifetime, or all of that, but the industry has not publicly stated the mix of those causes. Suspicions are growing, though, that like an old car, some reactors are no longer worth fixing, or fixing them is too risky a bet that nothing expensive will go wrong for a long time. And last year, U.S. utilities bit that bullet and terminated 14 operating or planned units, and many more are clearly at risk of closure this year. Now, this rise in real operating costs, chiefly for net capital additions, here shown in blue, and I've added the last two data points, steepened in '08 and again in 2011, despite major improvements, very commendable improvements in the industry's operating prowess and institutional learning. That seems consistent with age-related deterioration being a or the dominant cause, but we don't know yet till they release more data. Of course, since the operating costs driving the shutdowns are a small fraction of the capital cost of building new reactors, their economic case is even weaker, especially because their capital costs have stood up on end. Now, this graph is in the format pioneered by Professor Mark Cooper at Vermont Law School, and it combines the historic evolution of the real overnight capital cost paid per net installed watt. It's the yellow dots from Coomey and Holtman, with the evolution of projections from various sources. And the apparent very rapid escalation around 6 years ago turns out to have been due not as claimed to the run-up in commodity prices, which would only explain about 1% of the total project cost, but rather to shifting definitions. These early low estimates were marketing claims by vendors and promoters, but they were variable costs. The buyer would take all the price risk. The later estimates were firm or fixed costs where the seller takes most or all of the price risk, so they have an incentive to estimate more realistically. Amid such steep escalation and prohibitive capital cost, as the industry's Steve Kidd rightly said, nobody really knows what new reactors would cost to build. Now, impressively low construction cost has been claimed for some new Korean and Chinese reactors, but not yet transparently demonstrated. So the capital markets have not chosen to bet their own money. Since August '05, the U.S. has offered 100+% construction subsidies for new nuclear plants, plus operating subsidies slightly bigger than wind power gets, without making a single reactor financeable with private risk capital. Unfortunately, despite talented and devoted effort, nobody has yet shown how to overcome these prohibitive costs. No country has yet demonstrated a learning curve where building more plants makes them cheaper. The French program's more than doubled real capital cost and construction time resembles the U.S. escalation, whose fundamental cost, driven by the growth itself, was understood decades ago. Now, advocates of small modular reactors claim that series factory production can overcome their probably higher capital cost. Reactors don't scale down well as a matter of physics, but there's no evidence yet that this is true. Even if it were, small modular renewables, which do scale down well, are already decades ahead in exploiting their enormous economies of mass production, which I'll show in a moment. So reactors, I think, could never catch up. Hypothetical new or usually revived old kinds of reactors can't win either, because if the nuclear roughly 35% of the total plant capital cost were free, the non-nuclear 65% or so would still be grossly uncompetitive, as we'll see. But uncompetitive with what? That's the crux. The nuclear industry claims that its only realistic competitors are other central thermal power plants burning coal or gas. But in fact, the evidence shows that those arguments for excluding other competitors are not valid, and that all central thermal plants cannot compete in the U.S. or probably anywhere else with three other things: end-use efficiency, no or low carbon cogeneration, and carbon-free modern renewables. So I will next summarize those overlooked but potent competitors: cost, reliability, speed, and cost effectiveness for displacing fossil carbon emissions. Now, the cheapest competitor is more efficient use of electricity. U.S. use of electricity peaked in 2007 and then fell 2.4%, while real GDP grew 6%. In 2012 alone, almost unnoticed, the weather-adjusted electricity used to make $1 of real GDP fell by 3.4% in 1 year. That's equivalent to increasing U.S. nuclear output by 130 terawatt hours, or 1/6, in a single year. So utilities' new normal is stagnant or declining demand as efficiency outpaces economic growth. And the resulting revenue erosion is going to heighten incentives for utilities to push decoupling and shared savings, accelerating utility efficiency efforts, which were $7 billion last year, just as occurred for natural gas when they suffered demand destruction. As we will see later, over 4,000 years of program years of experience in 31 states, written up recently by LB&L, revealed average costs of efficiency around 2 cents a kilowatt hour. Well-designed megawatts actually cost a third as much now as they did in 1980. And that's especially true when integrative design is included, as it often makes very large savings cost less than small or no savings, turning diminishing returns into expanding returns. That's how our retrofit of the Empire State Building is saving 2/5 of its energy with a 3-year payback. It's how our latest deep retrofit of a big office building is saving 70% cost effectively. It's how our reinventing fire analysis found that a 59% reduction in U.S. electric intensity would cost only 2/3 of a cent per kilowatt hour. That's based solely on private internal costs and benefits, and everything met market hurdle rates. So we showed there how U.S. buildings' energy productivity, and buildings use 3/4 of our electricity, could triple to quadruple with a 33% internal rate of return, while industrial energy productivity could double with a 21% internal rate of return. So no wonder International Energy Agency estimates the world's investing about $150 to $300 billion a year in energy efficiency, and that is still a gross underinvestment. As for modern renewables, here on a logarithmic scale are the declining real market prices of photovoltaic modules in blue and wind farms in green. Mass producing these modular renewables makes them cheaper, so they grow faster, so they get cheaper, so they grow faster. In 20 states today, entrepreneurs can put solar power on your roof with no money down and beat your utility bill. Soon they'll offer cash back. Some recently contracted utility-scale solar systems have a total installed cost of $1.50 a watt, and some developers expect to be at or below $1.30 a watt by year end, as they apply and improve the streamlined installation methods already widespread in Germany and Australia. So that's how last year Solar Cities' installed system costs fell 30%, even though their module price ticked up by 3%. Already 10 or 15% of the houses in Hawaii use solar power, and many of them are dropping off the grid because at their prices, solar power plus full distributed battery storage is cheaper than staying on the grid. RMI's new report, The Economics of Grid Defection, show such virtual utility or utility-in-a-box offerings will reach retail grid parity across the country well within the lifetimes of existing utility assets. Now, if you want to know what modern renewables cost, look at the power purchase agreements that profitably sell their output. These are for U.S. photovoltaics on the left, wind power on the right. Typically, those power purchase agreements are written at constant nominal price and hence declining real price for 25 years. And they empirically show dramatic and continuing price drops. Solar power last year sold at levelized prices around 5 to 5.5 cents a kilowatt hour. It's now just below a nickel. net of a 30% federal subsidy, so that would correspond to an unsubsidized price around 7 cents and falling. Midwestern wind power last year, these purple circles, sold for about 2 or 2.5 cents and falling with federal subsidy, or that would be 4 or 5 cents without it. These prices are consistently beating new combined cycle gas plants on levelized cost in the marketplace today. By the way, grid integration of variable renewables typically adds a few tenths of a cent, even for very large, say, wind fractions, and they're probably lower than the uncounted grid integration costs of central thermal plants. Yet, many people still claim that solar cells and wind power, the two variable renewables, are too variable to produce much electricity reliably because we can't cheaply store huge amounts for when the sun doesn't shine and the wind doesn't blow. That's a myth. We do not need a storage breakthrough, nor do we need supposedly 24/7 or baseload coal and nuclear plants to keep the lights on. America's chief utility regulator actually said so 5 years ago, and let me explain why he was right. First of all, variable does not mean unpredictable. We can predict solar and wind power at least as accurately as demand. In this stormy winter month, the forecast output of all the French wind farms almost exactly matched their actual output a day later, and the small remaining errors vanished in the hours before actual dispatch. Second, we built the grid because no kind of power plant is actually 24/7. They all break. The giant plants are shut down typically around 10 or 12% of the time, losing 1 billion watts in milliseconds, often for weeks or months, and often without warning. The grid handles this intermittence as it was designed to by backing up failed plants with working plants. And in the same way, the grid can manage, often at lower cost, the forecastable variations of solar and wind power by combining them with renewables in other places or of other kinds. So let me illustrate how this can work. The varying loads on the isolated Texas grid get smaller and less peaky with profitable efficiency, as assessed by the national academies. So let's now make all of this with renewables, 86% with a mixture of wind and photovoltaics, real data, you can see how variable they are, and the other 14% with other dispatchable renewables. So that would be geothermal, small hydro, solar thermal electric with heat storage so it can run into or through the evening, burning feedlot biogas, urban waste, and obsolete energy studies. And the resulting diversified all-renewable supply leaves surpluses to charge up ice storage, air conditioners, and smart electric autos, which I've assumed here are fully built out by 2050. Then recovering that distributed storage when needed and filling the last gaps with unobtrusively flexible demand makes all the moving parts fit together. Now we have 100% renewable supply every hour of the year with no bulk storage and with only 5% left over. And using such choreography, some European countries, without adding bulk storage, are already delivering 25 to 58% renewable electricity, far more reliable than America's. By the way, Iowa and South Dakota are also over at 1/4 wind power today. So they in Europe have already far transcended renewable power's supposed reliability limits, and whatever exists is possible. The National Renewable Energy Lab has also choreographed reliable 80 to 90% renewable electricity for the lower 48 states. So bottom line, bulk electricity storage and fossil fuel backup are the costliest flexibility resources. They're up at the end of the flexibility supply curve, so we would use them last, not first. A breakthrough in cheap bulk storage would be very helpful, but it's not vital. We need not wait for it, and the market isn't waiting. Also, about 98 or 99% of power failures originate in the grid, so distributed supply that bypasses the grid can boost day-to-day reliability. Denmark has almost completed its transition from centralized thermal plants, mainly burning coal, to distributed wind turbines, this constellation of little blue dots, 86% owned by farmers in their communities, and cogeneration in brown, often burning ag wastes. Partly in consequence, Denmark has Europe's most reliable electricity, a little ahead of Germany's, and about 10 times more reliable than America's. Denmark is also reorganizing its grid into a highly resilient cellular architecture that makes cascading blackouts impossible. A similar approach reduced Cuba's serious blackout days from 224 in 2005 to 0 in 2007, and then sustained vital services the following year when 2 hurricanes in 2 weeks shredded their eastern grid. In contrast, the normally reliable nuclear fleet's occasionally unresilient behavior is illustrated by Fukushima Daiichi, and 4 years earlier by the earthquake that shut down the world's largest nuclear plant, the 7-unit Kashiwazaki Kariwa complex, some of which is still down. It's illustrated by mass deratings and shutdowns in US and European droughts and heat waves. And it's illustrated by the Northeast blackout in 2003, which some of you will recall. As shown here, 9 US reactors were running perfectly when the blackout occurred, so for safety they immediately scrammed. For the first few days they produced practically nothing, and it took 12 days to get them back to full power because xenon and samarium poisoning were robbing the reactivity needed for restart with stable and homogeneous neutron flux. So this anti-peaker attribute of being assuredly unavailable when most needed has no parallel in diversified portfolios of modern renewables. Next, let's examine recent claims that only nuclear power can scale up fast enough to meet global electricity needs or protect the climate, or both. The data show the opposite. Worldwide, starting in 2008, half of the new generating capacity added in the world has been renewable. And this graph shows the amount of wind and photovoltaic capacity added worldwide in each year. It's not cumulative installed, it's the net additions each year. So in 2012, renewables were half of US, over 2/3 of new European capacity. So America now has more solar jobs than it has steel or coal jobs. Also in 2012, China generated more wind power than nuclear power, and more new electricity from non-hydro renewables than from fossil plus nuclear. And last year, China added more photovoltaic capacity than the United States has, and we invented the stuff. In each of the past 3 years, modern renewables like these got $250 billion of private investment and installed over 80 gigawatts. In 2009, they surpassed the total global installed capacity of nuclear power, whose dwindling net additions, as I showed earlier, had turned negative even before Fukushima. In contrast, global orders for nuclear and coal plants keep fading because they cost too much and have too much financial risk to interest investors. Gas plant investments have held up better, but only because most buyers foolishly bet on the gas's bare commodity spot price without including the market value of price volatility, which roughly doubles the risk-adjusted price. They made that mistake 3 times before and lost their shirts each time. Now, cogenerating electricity with useful heat is another big competitor to central stations. And cogen combines with non-big hydro renewables to make up what The Economist magazine calls micropower. Since 2000, micropower has more than swapped its share of global electricity generation with nuclear power. Now, because the cogen data are sparse and quite inhomogeneous, I won't further analyze cogeneration here, but that's a major conservatism because it's already outproducing nuclear power. It has a strong business case, it continues rapid growth, and it's low or no carbon depending on its heat source. Definitions of installed nuclear capacity depend on uprates and re-rates, on whether and when retirements are counted, and on whether one assumes, as the IAEA does, that all 50 gigawatts of Japanese capacity that have been shut down for a couple of years will return to service, even though their owners think at least 30 gigawatts won't. But under all definitions, nuclear capacity has at best held steady over the past 7 years, while renewables, excluding big hydro, have tripled their capacity. Now, the average kilowatt of nuclear capacity, of course, produces about twice as much annual electricity as the average kilowatt of renewables other than big hydro. But based on these global trends, the non-hydro renewables, which the nuclear industry does not even acknowledge as a serious competitor, should surpass its annual electricity production within the next year or two. And this is happening because mass-produced renewables scale up in a fundamentally different way. Traditionally, we built giant cathedral-like plants costing billions of dollars, taking best part of a decade. The average nuclear plant in the last decade has been 9.5 years. But now each year you can build a factory that each year thereafter produces enough solar cells to produce each year thereafter the same gigawatt year of electricity that your cathedral would have produced. So there's a factor 15 difference in cumulative production over the first decade in this illustration. And that's why the solar output scales up incredibly fast. It's why solar cells are growing faster in the world than cell phones. Indeed, modular short lead time technologies accessible to many market actors can add more total capacity sooner than big long lead time technologies requiring special institutions. Now, the motto in my shop is, "In God we trust, all others bring data." So here are some data. Since 1950, the nuclear unit count and capacity that the IAEA lists as under construction worldwide has peaked, declined, and modestly rebounded. So that's the nuclear renaissance you heard about. And the 72 units so listed, including about a half dozen listed for upwards of 20 years, are 68% in 4 centrally planned and rather untransparent power systems, namely China, Russia, India, and Korea, often building designs with unknown Western licensability. Another 5 U.S. units are underway and enjoy special non-market conditions. 10 other countries have 1 or 2 units each. Many of these 72 under construction units are late, probably boast. Most of them have no official startup date. Not a single one was chosen by a competitive or analytic process that fairly compared them with the slate of available alternatives. But leaving economics aside and focusing solely on speed, on logistics, what got built in nuclear power's most aggressive phase when the under construction slope was steepest? Well, the peak year was 1985, when it added nearly 32 gigawatts, and the best 3-year period was 84 to 6, when it added almost 92 gigawatts. In the best year and 3-year period so far, the non-hydro renewables have added respectively 85 and 249 or so. So they've added capacity 2.7 times as fast as nuclear ever did. And because the capacity factor difference is less than 2.7, it's closer to 2, the renewables actually added more electrical output than nuclear did during those peak nuclear periods. Now, comparing graphically the electricity output since 1950, we see that the steepest part in here of nuclear's output growth curve had a similar slope to the recent steep part of non-hydro renewables growth curve. But then, of course, the nuclear growth flattened and reversed as its costs rose for the reasons explained in the 80s that are dependent on its growth, while renewables are growing ever faster as their costs fall for equally durable reasons dependent on their growth. Now, if we add the output from small hydro, for which we only have data through 2011, you can see even stronger growth for all renewables excluding big hydro, which, by the way, is even larger, also growing fast, but I've omitted it here as a conservatism. Now, if we then dig into the national level, the nuclear histories of Sweden and France and Belgium show a number of milestones for decades of institution building and capability building before you could get significant nuclear output. In contrast, as we see for Germany, for example, mass-produced renewables can get out of the starting blocks far sooner by exploiting globally marketed commodity equipment, fungible installation skills, rapidly evolving business models and finance channels, and choices by millions of diverse actors, or in the case of China, a determined central government driving aggressive, mainly private industry. China's output from renewables, excluding all hydro, matches in slope that of the other triumph of central planning, the French nuclear program. And if you add the Chinese small hydro, in which they're the world leader, it's about to surpass the French nuclear output level. So these two countries show broadly comparable slopes of electricity production growth for the world's most aggressive nuclear and most aggressive renewable, non-hydro renewable programs. Also, Germany's renewables, a quarter of consumption last year, already far outproduce Europe's most ambitious nuclear programs, except, of course, that of France, whose policy for 40 years was not to maximize competition, but to prevent it. Now, here's the different lens on those data. After a long wind-up and initial growth spurt, the Swedish and French and Belgian fraction of consumption of electricity, not production, but consumption, served by electricity, held up for a long time. It's slipping a bit, while the renewable share in Denmark, Portugal, and Spain is growing to respectable size, even without hydropower, which would bring Spain to 45% and Portugal to 58% last year. But these graphs do not show two other big competitive and fast-growing distributed resources that compete with nuclear. Namely, we should look at renewables plus efficiency plus cogeneration, all growing together and stacked up. And they are far faster than renewables alone, and together they leave any central station solution in the dust. So if we had better negawatt data, we could actually graph that trifecta. Nuclear also has the burden of having to run ever faster to stay in the same place, as its 1970s and 80s growth curve we saw earlier is echoed in a retirement bulge that after the next few years will exceed all of the planned or conceivable global nuclear growth, even with all license extensions, as shown here. Power terminals' terminal decline will be, or power reactors' terminal decline will be over by about 2060. And in the view of both competition and aging, I think it's more likely to decline faster than this than slower than this, but time will tell. Now, nuclear power's commercial collapse, finally, is actually good for climate protection. And to explain why, I'll conclude by examining the view almost universally held, even among critics, that new nuclear build could help protect the world's climate. My colleagues and I have pointed out for 3 decades, but the business press has never covered, that this is untrue for a straightforward reason that economists call opportunity cost. Fancy way of saying you can't spend the same dollar on 2 different things at the same time. So let me explain how that works. Displacing a kilowatt hour of coal-fired electricity displaces the same amount of carbon emission regardless of which carbon-free substitute is shown. Gas-fired generation, shown here, also emits carbon, but less than coal. So gas plants can also save carbon if you don't leak too much methane. So I've shown some sensitivities there to methane leakage end to end. Carbon-free substitutes, whether they are nuclear or efficiency, which I'll quantify later, or modern renewables, would all be equally advantaged by pricing carbon, but they are not all equally effective at saving carbon for two reasons. First, technologies that can be built sooner and scaled up faster will save more carbon over time. And second, technologies that save more carbon per dollar invested will buy more solution. And nuclear power doesn't do well on either of those tests. To see how, we have to look at the different economic costs of different ways of displacing coal-fired electricity. So here I've compared a range of current costs of delivered, that is retail electricity, using Lazard's conservatively low estimates for thermal plants, especially nuclear, where the latest reality check is the proposed new British station after subsidies that the EU says may cost more than the plant. Now, farther to the right are the empirical market costs, the power purchase agreement ranges I showed, empirically discovered in the market for utility scale solar and wind, and then the same quantities with their federal subsidies backed out. And those temporary subsidies are generally less than the permanent subsidies received by the thermal plants. At the far right are placeholders, which I'll fill in presently, for the costs of using electricity more efficiently. So now let's take the reciprocal of these cents per kilowatt hour costs of delivered electricity, turn them upside down, and that gives us the number of delivered kilowatt hours that you can make or save by buying a dollar's worth of each alternative. Finally, let's combine that graph with the earlier graph of how much coal-fired carbon each kilowatt hour displaces. And then we'll be able to see how much carbon we can displace by investing a dollar in each alternative. And here's the result, that new build nuclear power's market price makes it about as cost-effective a carbon saver as a new natural gas combined cycle plant with about 1.5% methane leakage, or about 3 to 5 times less cost-effective than new solar or wind power in good U.S. sites. Cogeneration, by the way, is not shown, but it typically ranges from about 4 times better than nuclear if it's gas-fired and in buildings, less than 4 if you have methane leakage, to about 10 times better than nuclear or more with methane leakage if it's run instead on industrial waste heat that was otherwise being thrown away. Thus, as the costliest option, new nuclear build is the least effective supply-side carbon saver per dollar, and also per year, because as we saw earlier, it's slower than its cheaper competitors. Now, in order to show the costs of the best buy, energy efficiency, which beats any kind of supply, we have to rescale the whole graph, and then those differences between supply-side options become pretty small in comparison. Here are the recent data on the measured costs of efficiency for various applications. The measured utility program costs are listed in boldface. The lightface are some detailed empirically based analyses of the average cost of saving far more electricity than U.S. reactors make. But either way, efficiency is clearly cheaper than average nuclear operating costs, which exceed 4 cents a kilowatt hour at the bus bar or 8 cents delivered. These average about 2 cents. So overall, for saving coal plants carbon, efficiency is about 10 to 50 times more cost effective than the new nuclear build. So whether you choose efficiency or cogen or renewables, just being nearly carbon-free does not make new nuclear build an effective climate solution. Rather, because it saves about 3 to 50 times less carbon per dollar than its main competitors, and it deploys slower, new nuclear build would reduce and retard climate protection. See, if climate is a problem, we have to invest judiciously, not indiscriminately, to get the most solution per dollar and per year. Anything less makes the problem worse. Nor do we need nuclear power to offset PV's and wind power's variability, or to scale faster than renewables, or to save or make money, because as we've seen, nuclear power can't do any of those things. So there is no reason beyond ideology to build more nuclear plants. Capital markets, seeing big new costs without offsetting benefits, long ago reached the same conclusion. The existing nuclear plants, a worthy future idea whose time has passed, will simply retire in due course, and the only choice is how quickly and at what cost to whom. End of story. Thank you.
Well, thank you, Amory. Why don't we open things up with some questions? And there is one I want to ask before we finish. Right here.
So the cost per watt of solar, of installed solar capacity you mentioned is, I mean, when I talk to solar integrators here in New Hampshire, we're still getting like $370 a watt or $345.
That's probably rooftop, right?
Yes.
Yeah, which costs more than ground mount utility. Although, interestingly, the average installed system cost for all photovoltaics in Germany last year was about half of ours, even though we all buy the same equipment. But they'd scaled installation to as much as 8 gigawatts a year, and they have 35 gigawatts installed. So they have streamlined the process a lot more, and they have a one-page single application form. In California, you might have a couple of dozen big forms. So there's a lot of transaction cost.
Did you have a follow-up to that?
Well, I mean, if that's
But I was going to say they're 70% rooftop, so they've even made those cheap.
No, you can go ahead. That's good.
Yeah. And of course, we've had time and motion teams swarming over Germany and Australia, seeing how they do it, and now the U.S. installers are catching up and even perhaps pulling ahead.
One of the things I had expected to hear is part of the arguments with externalities and the cost of externalities, which are not included in any of your calculations, and think would even augment your case even more. When you talk about
Correct.
how do you deal with the waste, how do you deal with resolving coal outputs and so on.
Well, and neither did we include here any other externalities, climate or anything else. And those are big, like electricity and oil are currently unrelated 99%, but it's noteworthy that we spend $4 billion a day on the hidden economic and military costs of getting $2 billion a day worth of oil. And I'm not counting there any harm to health, safety, environment, climate, global development, global stability, or our nation's reputation and independence, all of which are worth something. We've conservatively counted all those at zero. Conversely, we counted at zero the positive externalities like energy resilience, happier, healthier, more productive people in efficient buildings, and so on.
Can you explain what fuels a zero or low carbon cogeneration system, please?
Yeah. The industrial waste heat can be renewable or non-renewable. It's typically natural gas today. It could become what is called green gas. It may well become solar process heat, although as a conservatism we didn't count any of that, and some of it is actually in the money right now and being used for enhanced oil recovery in California. Directly fueled cogen, same slate. It can be renewable or non-renewable. There, for example, the forest products industry essentially makes its own electricity from hog fuel and black liquor, stuff they can't otherwise use. And the furniture industry gets a fair amount. There's quite a lot of cogen in the refinery business run from various waste gases and light hydrocarbons they can't otherwise use. So it's a very complicated picture. But again, I didn't count cogeneration in these charts. That's a pretty major conservatism.
No, I'm from Denmark actually, and I know that even though we have a big share of our electricity coming from wind power, we still need other resources for peak hours. And what do you think will? I mean, at some point we'll face some diminishing returns of investment on more wind power. So, We still need.
Well,
even-
haven't hit them
even though
yet, your
you-
costs are still coming down.
Yeah, but even though the U.S. would invest a lot in wind and solar power, they probably still would need other energy sources to cover those peak hours.
Yeah, let's see, let me just summarize what we found in here, since this is about the U.S. We showed here in a very empirically grounded way, very case-rich and data-rich, how to run a 2.6-fold bigger U.S. economy in 2050 with no oil, no coal, no nuclear, a third less natural gas. It would phase out over the subsequent decades, but not by 2050. Tripled end-use efficiency, 3/4 renewable supply, up from about 1/10 today, and we found this would cost $5 trillion less in net present value than business as usual, counting all externalities at the conservatively low estimate of 0. And this would require no new inventions and no act of Congress, but be led by business for profit. We did not count feedstocks, but only fuels. So the feedstocks, and I agree with National Academy's reports on this, are quite likely to have gone over to biologically based molecules by 2050. That's going pretty fast right now. And we will have a lot more closed loops and more elegantly frugal use of materials. Does that help? Now, Denmark's a very small country, and yet in some way it is the most advanced in grid integration, in energy policy and in efficiency. So thank you for that good example.
Electricity in Europe.
I'm sorry?
It has the most expensive electricity in Europe.
Now, have you noticed that that's mostly tax? It is. Look at the numbers. Yeah.
I've looked at them.
It is mostly tax. Similarly, Germany has high household electricity prices, which are half taxation, and the wholesale prices are very competitive in Europe. They're the only consistent net exporter to France, and they've dropped the wholesale price about 2/5 in the past 5 years. It's continuing to drop. So when you discuss prices, please be very careful about what you're counting. They have a policy in Denmark of taxing electricity. That's a legitimate way to raise revenue and signal the value of a resource. It's their choice, not mine. But the wind has clearly reduced their wholesale power cost. And this is exactly the same phenomenon you see in Germany, where it's destroyed the business models of the major utilities that thought it wouldn't happen, not for lack of warning them, which I did, many others did. But it's undercutting their fossil plants, and that was perfectly predictable. It's just the same we see in the Midwest that Daniel talked about earlier.
Right here.
Amory, I think I understand the argument about increasing cost of either wind or solar-based in the commodities, the actual units. But at some point, how do things like available land, transmission distance, factor into your economic analysis?
Yeah. Well, we used the same Reed's model that NREL used in its REF's study of 80 or 90% renewables, except that we looked at half distributed, whereas all of their renewables were centralized. Therefore, we needed a lot less transmission than they did. We did look carefully at land use and found that although there are, of course, some specific siting conflicts in specific places, the actual land intensity is not greater for modern renewables. There's a good paper on that. It is the same for photovoltaics if they're ground-mounted as it is for the nuclear fuel cycle, according to Argonne's assessment, I'm sorry, Brookhaven's assessment. If it's on rooftops, it's no land, and then in the case of wind, it's several orders of magnitude less than that.
I understand that, but are you assuming unlimited, so that as long as you can build, you can find a place to build? Is that how the model treats?
Well, the reason I don't think it's a very good question is that U.S. cost-effective lower 48 onshore wind resources, onshore and nearshore, I guess, are about 19 times U.S. electricity consumption. And you think you could cite 5% of the resource? I think that shouldn't be very difficult. But you're not going to meet it all from wind anyway. It's a diverse portfolio. And you will have, just as the NREL thing showed, a mixture of lots of different ones. In fact, I'll play you a different NREL one. This is the evolution from fossil and nuclear in black to a mixture of renewables going from 2010 to 2050. This takes them up to about 2/3 renewable on an annual electric basis, and they did go as high as 90% in their analysis. So it's different stuff in different places, but they designed this to fit the transmission system and add a little more. Now, a fascinating thing about this, take a look around Chicago. They're not actually doing much, if any, wind in Lake Michigan, but that's actually an equal or better resource compared to bringing, say, Montana and Dakota wind to Chicago. You have to pay for ice and marine engineering and a cable, but you don't have very long transmission lines. And we're finding similarly with the offshore wind, that's enough to run the northeast coast. A middling renewable resource near the load center will often have just the same economics, sometimes better, compared to a first-rate renewable resource far away. So the conventional view that you have to do solar in the desert southwest and wind in the high plains and then run thousands of miles of transmission lines is turning out not to be true. Exactly the same has turned out in Germany. There was a great paper on this from Agrar Energiewende showing that most or all of the planned transmission additions are not necessary to get the same economics from more local resources.
I'm going to get the last question, and then we've got to wrap up.
I'll be around the rest of the day.
So what if the historic price volatility of natural gas is not borne out in the future? There is a school of thought that this abundance of natural gas is going to change that dynamic.
That's a very nice question, thank you. And we did not prearrange this. So,
Boy Scouts honor.
Yeah, let's see, where did I put that? Here we are. So here's the historical record where the green is the real Henry Hub price and the blue is the EIA forecast of that quantity. And investors one time lost $100 billion on mistimed combined cycle plants, and they've actually lost money 3 times and about to be 4 in the past 20 years by betting that they can ignore volatility. Funny thing, it turns out if you have abundant, stable wellhead gas, it probably increases the price volatility downstream by driving at least 3 kinds of supply-demand disequilibria, namely LNG exports, petrochemical pivot to gas, they're very good at that, and of course downstream infrastructure owners exploiting bottlenecks like pipeline capacity and earning a rent on that. So if you are comparing gas with a constant price resource like efficiency or renewables, both common sense and financial economics elementary course will tell you you have to risk adjust, you have to count not just the bare spot price of the gas commodity, but also the market value of its price volatility, which you can discover by the straddle in the options market. When you do that, it roughly doubles the gas price. Then you're looking not at $3 or $4, but at $6 or $8 gas, which happens to be just what the futures market says it'll cost a decade out. That makes sense for 2 reasons. One is markets equilibrate. So if you want $6 or $8 gas, assume $3 or $4 gas and use it accordingly. Second, there are about 8 major risks and uncertainties around fracking, which will take a decade or so to play out. And if they are all satisfactorily resolved, we'll have a longer, lower, flatter supply curve for gas than we used to think, and optionality is good. As a member of the National Petroleum Council, I hope that works. However, 8's a pretty big number, so I wouldn't bet a lot of money on all of them coming out right, in which case we won't be unduly disappointed because we weren't going to need that much gas anyway. So I think there is an important story in fracking around abundant and affordable energy for the long haul, except the story is a lot less about gas than about its physical hedges, efficiency, and renewables that are outpacing it and increasingly outcompeting it.
On that note, thank you, Amory.